In the last video, I've talked about how in a rotating coil, the components of a uniform field that is going through a coil, how the component perpendicular to the coil depends on cosine of the angle between the field direction and say a direction that is perpendicular to the coil. Now this leads to a flux density, leads to a magnetic flux linking the coil that depends on cosine of this angle, which is here, of this angle, so that if we have a coil that is rotating uniformly, meaning at a constant angular velocity, then the flux would change with time following a cosine curve. What I'd like to do in this video is to look at how this affects the induced voltage, how the voltage changes with time. Now the simplest way to understand and to actually find out what the voltage looks like is to think back at what we have learned for simple harmonic motion. Now recall that in simple harmonic motion, let me take a simple example where I have, say, a spring attached to a support, and I have a certain mass here. Then when I pull this down and let go, the mass would oscillate up and down. And suppose that this is the x direction with the 0 at the rest position and the upward direction as positive. Then we have seen how we can describe this oscillation using a graph. Time on the horizontal axis, x on the vertical axis, and the graph could look like a sine curve. Okay, and we would represent this by say x equals to x naught sine omega t, for example. And then if we want to find the velocity, if you want to find the relation with the velocity, what we do is we think about how x is related to velocity. So velocity is equal to the change in the displacement. If I think about delta x to mean the change in displacement over a short time delta t, that will give us the velocity. And we have learned from displacement time graph, x here is the displacement, that the gradient on the graph is the velocity. And we can relate this to this meaning of the velocity quite directly. If we think that let's say for a short time delta t, let's say from here to here, let's say that's my short time delta t, x changes by delta x. So this is my change in x over this short time. Okay, This is the change in x when the time changes by a short amount. And the change in x over the change in time on the graph is simply the gradient of this part of the graph over this short time interval. And that is why the gradient of the displacement time graph is the velocity. And we have seen how the velocity time graph for simple harmonic motion looks like. We've seen how to relate it to the displacement time graph. And the way to do it is to look at the displacement time graph and say that right at this point, okay, let me put in some marks here for the time. That's the time for one period. So, for example, at this point where the gradient of the displacement time graph is horizontal, that should be v actually. At that point, the instantaneous velocity is 0. So, because the gradient is 0, so the velocity time graph would have a point here for 0 velocity, and down here is the gradient is horizontal again, so the velocity here is 0 again. Down here, however, at the start of this graph, we have a gradient, right? We have a maximum gradient, which gets more gentle as we move towards the top. So that means that the velocity is at a maximum at this point. Now, when we're down there, we also have a maximum gradient, but in the negative direction, because the slope slopes the other way, the opposite way from here. Okay, the displacement is going down, so we have a maximum velocity in the opposite direction. And down there it goes up again with maximum velocity. Oops, maximum velocity, that's up there. So I can, based on this, I can sketch a graph to see what the velocity time graph looks like. And as we have learned in simple harmonic motion, this is what it looks like. And the relation between the velocity time graph and the displacement time graph is that both looks like a sine curve, but the velocity time graph looks like it has been shifted. You can see the peak is there for the displacement time graph, but the peak is here for the velocity time graph. So it looks like it has been shifted by a quarter of a cycle. And we describe this velocity time graph using a cosine. You can describe it using a cosine curve, because that's what a cosine curve looks like. It has a peak at 0 angle. So the velocity time graph is described by this. Now the peak velocity, as we have seen in the top videos on simple harmonic motion, is omega, this omega here, times x naught times the amplitude. So the velocity equation, right, as I've said, it is a cosine curve, so it should be a cosine omega t. But because of this amplitude, we have to multiply by omega x naught. Okay, so that's what we have learned, right, from simple harmonic motion. Now we can apply this quite directly to the rotating coil. So let's take a look. We have a magnet that produces this uniform magnetic field. Okay, and we have a rotating coil. So that's my rotating coil. Okay, and think about direction that is perpendicular to the coil. That's just a normal direction. Normal as in perpendicular. And the angle between magnetic field and this normal direction is theta. Okay, and we think about theta as changing uniformly with time, so that theta is related to time by omega t, where omega is the angular velocity. Alright, and as we have seen in the last video, the magnetic flux, which is given by the perpendicular components of the magnetic field multiplied by the area of the loop. We've seen that the magnetic flux is given by phi equals to B times A cosine omega t. And we know how to plot the cosine curve. It looks like, let's say that's the period, time for one cycle. So the cosine curve looks like this. Roughly. Okay. Now the question now is, what would the velocity graph look like? As the flux changes, as the flux linking the coil changes, so velocity would be induced. Let's think about the relation between flux and voltage. Did I say velocity will be induced? I mean the voltage will be induced. So the voltage is related to the flux density by voltage is related to the flux by the change in flux divided by the time taken. So this is according to Faraday's law of electromagnetic induction. Now if you look at textbooks or Wikipedia on Faraday's law of electromagnetic induction, the equation that you see would have a minus sign in front. Okay. Now for now I shan't go into that detail, so I'm just going to ignore the minus sign and just take the value that I get from here to find out how the voltage changes with time. If I compare this velocity equation with this voltage equation, you see that they're very similar. The difference is that instead of a change in displacement, I have a change in flux. Okay, and we have seen that for the voltage, for the velocity case, this relation, alright, because velocity is related to the change in displacement over time taken, the effect of this, the result of this this relation and this formula is that the gradient of the displacement time graph is the velocity, because this fraction or this ratio is basically the gradient. Right? If the time is short, this ratio is just the gradient on the displacement time graph. So in the same way, this ratio, change of flux over time, is just the gradient on the flux time graph. Okay, so let's say I take short time here, delta t, and the corresponding change in flux is here. So that's my delta phi. Okay, so delta phi is just a vertical change, delta t is the horizontal interval. So the ratio is therefore just a gradient. So therefore, according to Faraday's law, we can deduce that the voltage is just the gradient of the flux time graph. Now that is a very useful result. And I think I should write this down actually. The induced voltage is equal to the gradient of the flux time graph. Not sure if it's ever said in these words in any textbook, but it's something which we should find useful. So therefore we can use the same idea as simple harmonic motion to sketch our velocity time graph and even to get the formula. So let's try that. Now, if you look at this, that is maximum flux, so the gradient is 0. So therefore the velocity, the voltage is 0. That is minimum flux, so gradient is 0 again, and that's maximum flux, gradient is 0 again. So the voltages are 0 at these points. Okay. Now at that point we have a negative gradient, so the voltage has a negative maximum. At that point we have a positive gradient, positive maximum gradient, so the voltage is the maximum. Okay, so if I now sketch a graph, it would look like this. I can see that looks like a sine curve. Right? Maybe an upside down sine curve. That's a sine curve, that's a sine curve. It's an upside down sine curve. So if I want to write a formula for this, it would look like V is equal to V naught sine omega t. Right? Now, to be precise, for this graph, I should put a minus sign there. Okay, but I'm just going to leave it out because I'm mainly interested in the shape of the graph. Okay, and if I leave out the minus sign, it just means that this graph will look like it's either upside down, or if I start timing from, say, this point instead. So I'm just going to leave it in this form as a formula for the voltage that is produced by a rotating coil. Now one more detail to tie up here is this. It would be nice to know how this peak voltage is related to this maximum flux BA, and we can easily see the relation by comparing this maximum displacement with the maximum velocity. See, the maximum velocity is given by omega x naught, is given by this, the factor that multiplies the cosine. And if you compare it with the maximum displacement, see that we just need to multiply the omega, multiply the angular velocity by the maximum displacement to get the maximum velocity. So in the same way, we can get this maximum V0. Just this value here. If we multiply the amplitude of the flux amplitude, by the angular velocity. So omega B A. This would be the maximum V0. Write it down here. V0 is equal to omega times BA. And what this means is that if the rotational speed, if the angular velocity is bigger, the maximum voltage will be bigger, which is what we expect from Faraday's law. Because the faster the flux changes, if it rotates faster, the flux changes more quickly, therefore a bigger voltage should be produced.